All right, I'll go ahead and try to share my screen. Let's see. All right, can you see my screen?
Yeah.
Yes.
Cool.
Yes.
Full screen mode. So I don't know if I have 20 minutes worth of content here. I probably don't. But the idea is
problem.
that, so I hope to make this more of a living document to act as a reference that we can provide to mission teams that are interested in making the transition to Python. I think one of the big concerns right now is the fact that most of the developers on the mission teams actually don't know Python, and they're very familiar with IDL. So I was hoping to create a resource for them. And so if I'm missing something, or if there's something else that should be added, please either email me afterwards or bring it up during the presentation. And I'll go back and if we do have suggestions, I'll go back and watch the video later and make sure we get all of them into the next version of the document. And we can also add your names to the front page if you contribute. And so we have a list of contributors. So as a general overview, both IDL and Python are dynamically typed interpreted languages. So they're very similar outside of the cost of IDL. But the big difference for most IDL developers is that IDL has a single namespace, while Python allows you to have as many namespaces as you'd like with modules and packages. And I think every IDL developers run into this problem. So that's a huge benefit of Python over IDL right there. So you don't have to worry about the namespaces or worry about everything being in the same namespace. And another significant.
You can run SolarSoft and SpeedS at the same time.
Yes, correct. Or AstroLib and SpeedS. And so another significant difference is that variable names are case sensitive in Python, and in IDL, they're actually case insensitive. So you have to be on the lookout for that. And in Python, the control flows controlled by tabbing. While in IDL, the control flows, it's based on the function definitions or the procedure definitions, as well as begin and end. So I think the control flow is easier to follow in Python. And an important note is that many of the following slides assume you've imported NumPy as NP in your Python session, because we're going to use NumPy a lot to show how to do things. So here's just how to define a function in IDL on top, and how to define a function in Python. It's very similar. You just, in Python, it's just def and the function name, and you give it the input and then the keyword options. And a significant difference is that you set the defaults for the keyword options in the actual function definition. And generally in IDL, you would do that after you define the function and once the function starts running. And of course, return values in IDL have a comma, but you don't actually have to, we don't have that in Python. So arithmetic operators, they're all pretty much the same other than the modulo. So assignment is the same, addition is the same, subtraction, multiplication, division, and power, of course, is it's not the caret, it's star star instead of the caret. And of course, modulo is in IDL, it's mod, and Python, it's just it's the
Percent sign.
Percent sign, that's the one. Yeah, thanks. And of course, the relational operators are different. In IDL, it's equal, less than, greater than, less than, equal to, greater than, equal to, and not equal to. And in Python, it's like it is in most other programming languages, equal, equals, less than, greater than, less than, equals to, greater than, equal to, and not equal to. And for logical operators, they're the same pretty much for and or. But the logical exclusive or, you'll have to use, I couldn't find a logical exclusive or in the Python standard library, but we have one in NumPy, and it's just np dot logical underscore XOR. And both languages also now have ternary operators. I think this was relatively recently added to Python. But what happens here is if you have two different values, or if a variable can take two different values based on some statement, if statement, you can put it in one line. So in this case, if b is greater than 10, the value a is equal to 1. If it's not greater than 10, then the value is 2. So this is how you do this in Python. It's a is equal to 1 if b is greater than 10, else it sets it equal to 2. If else statements are much different, primarily because of what I mentioned earlier about the control flow. Since Python is just using tabs for the control flow, you don't have to have this then begin, end if, else if logic. You just say if a equals b, and then give it however many tabs you're using, and then do elif for a different condition, and then else for all other conditions. So it's much cleaner in Python. And for loops have the same benefit. You don't have to do the do begin end for. You just have your for statement and have your tabs to make sure the control flow is right. One thing to note is that when you do for equals or I equals 0 to 10, what this does is, so this is the start value, the end value, and then the steps. And to do the same thing in Python, we use np.arange. So we have the start value, the end value, and the steps. And notice that this is 11. That's because in IDL, this is inclusive, and in Python, this one is exclusive. So technically, these two do the same thing. So if we had 10 here, this would only go up to 9. And so both languages have hash tables now, which are just dictionaries. In IDL, you just call hash, and you give it the keys and the values, and then you can reference them just by hash table and then the key. And Python is very similar. And of course, you can also use a dictionary, the dictionary function to create a hash table. But this is the way I tend to do it. And actually accessing the values from the keys is the same in Python as it is in IDL. So if you're looking for standard math tools, I know there's a whole bunch more that I'm going to have to add to this, but most of them are in NumPy. So the equivalent of square root is just np.square root, and the natural logarithm is just np.log, and then the log base 10 is just np.log 10, and then exponent is just np.exp. And if you want to create some arrays, so if you want to create a list of 5 array or integers, you have to use NumPy. So it's numpy.zeros, and give it the number of integers you want to create, and you actually have to set the data type to integers, which is stored also in NumPy. And if you want to create a double array or a floating point array, in this case, you don't actually have to set the data type. It defaults to 64-bit floats, but I wanted to specify it here just so it's clear that it's np.float64. If you want to create an array of 1s rather than just 0s, in IDL, you create the array and then you just add 1, and because since it's going to be all zeros, add 1 to the zeros, and it's all ones. But in Python, we have numpy.ones to create a list of ones. And just like with the other zeros, you can create, if you set the data type to bool, you can create a Boolean array. So those are all just true falses. And if you want to create an identity matrix in IDL, it's just identity and then the size of the matrix. So this would be a 3x3 identity matrix. And in Python, again, it's just np.identity and 3. And you want to create a diagonal matrix. The off diagonal terms are all 0, and the diagonal terms are these. So it's 1, 2, and 3. In Python, it's just np.diag. And what about sequences? If you want to generate sequences, I showed a range earlier in the for statement. So it's essentially the same as the INDGen. This generates integers, or 10 of them. And so it's np.arange. And if you want to create floats, in IDL, it's fngen. So in Python, it would be, you just set the data type to np.float or np.float64. I think np.float is just essentially a placeholder for np-float64 right now. And if you want to generate a sequence and that actually, that vary, in this case, we use intgen to generate 4 numbers. Each one is multiplied by 3 and then added 1. So that generates 1, 4, 7, and 10. To do the same thing in Python, it's just np.arange. We start at 1 and go up to 11, but of course this is exclusive, so it doesn't include 11. It just goes up to 10 in steps of 3. So it's 1, 4, 7, 10. And for slicing, so this is one of the more significant things that we have to really consider. So in this case, before we jump in, I define an array or a matrix that looks like this, and note that the numbers are the row and then the column. So 1, 1, 1, 2. This is row 1, column 3. And to create the same array in Python, you do np.array. And we're going to use this on the next slide. So that same matrix is up here on the top. So if you want to access item 2, 4, that's row 2, column 4. So that would be this 2, 4 that's bold right here. In IDL, it's 3 and 1. So you have to go 1, 2, 3, and then down 1. But in Python, it's the exact opposite. So it's down 1 and then over 3. And if you want to print the first row, so since they're flipped, in IDL, you do the star in the first, and then just give it a 0, and that would print that first row. And in Python, it's 0 and then colon, and that prints the exact same thing. So I usually just think of them as being the opposite, flipped. And of course, the first column is the opposite of that. So it's 0 and then star. And that would put this 1, 1, 2, 1, 3, 1. And to do the same thing in Python, it's colon and then 0. So that's one of the biggest hurdles is when working with the numerical data and doing the transition, is knowing that these are backwards. And what about rounding? And IDL, we have, of course, round, then we can round up with ceil and then round down with floor. And NumPy has routines that do the exact same thing. So it's np.around for rounding, and then np.ceil for rounding up, and then np.floor for rounding down. And for matrix multiplication, so if you have 2 matrices, A and B, In IDL, you just use the hash a hash hash b to multiply them. In Python, NumPy has a routine, matmul. Let's give it a and b, and it multiplies a by b. And if you want to do a dot product, in IDL, you have to transpose a, and then so this is a vector dot product of two vectors. So the way of doing it is transpose a and then do the hash b. But in Python, it's just v dot from the NumPy package. And a cross product in IDL is cross p. And in Python, it's just np dot cross. And so if you're looking for constants, they again tend to be in NumPy. So you can also access them from the math library. But since we've been sticking with NumPy, let's show how to access them from NumPy. So in IDL, it's just pi exp, and for NaN values, you have to use the value. You have to use the system values, which contain the fnan. But in Python, it's just numpy.nan. I think you can also say float nan as a string, and it also returns a nan. And of course, Python also supports complex numbers. So it's an IDL, it's a, and you give it complex 1 and 2. So that's the real part first and the imaginary part second. In Python, it's just a equals, and you do it just like you would in your math class. It's 1 plus 2j. If you want the absolute value, it's again just np.abs. If you want the real part, and once you have it defined here as a, you just do a.real and then a.imag for the imaginary part, so that would return 2. And in IDL, there's a function called conj to return the complex conjugate. In Python, you just run the conjugate method on your imaginary number or on your complex number. And so what if you want to generate a linearly spaced vector? So in this case, in IDL, you would use interpol, and that would generate, this would generate a linearly spaced vector from -90 to +90 with 16 elements. In Python, you just use the linspace method from the NumPy library. You give it -90, +90, and 16 elements, and that generates the exact same thing. And I included some resources here at the end that I used to put all this together. I'm hoping that others have more resources and more suggestions that we can add. One that I really want to add is rebin, because I think that's a one that doesn't necessarily exist in both IDL and Python. I've had to recreate that with numpy.repeat, but I haven't added it here yet. So if you have more suggestions for this, please let me know. I think everyone has my email, but I included it here at the top. And I also uploaded this to the meetings folder. So everyone should have my email now if you don't.
Thanks, Eric. Oh yeah, go ahead. We have time for one quick question.
Okay. Thanks for the presentation. I actually just made this transition from IDL to Python about 2.5 years ago. The main thing I found confusing at first, switching from IDL to Python, was the whole period notation, where different functions were attributes of an object. That was something I was hoping you would include. Maybe you could add that.
Oh yeah, that sounds good. Yeah, that's be a good addition.
Okay.
Looks like there's
Great.
several good suggestions in the chat too, so I'm gonna save those.
I also threw them in the meeting notes. That helps. All right. Well, thanks, Eric. I believe up next we have Brian Harder with setting up GitHub actions. Brian, do we have you?
Hello.
Hey.
Just a sec.
Oh, sure. Some point today, if you could upload your slides to the drive, that would be great. Thanks.
Oh yeah, sure, certainly. Okay, so
No
I'll be
rush.
going over GitHub Actions. So I'm certainly no expert, but I do use GitHub Actions on the Python projects that I work on. So I figured what I'd do is run through some slides really quick, just introducing it, and then we'd poke around my code repos, taking a look at how it works in action. So here, let's go into presenter mode. So what is GitHub Actions? So it's a GitHub tool that's built in that allows you to respond to events in your repository. It actually just started out as something called GitHub Apps, where it would send out notifications to your infrastructure saying like, oh, somebody just did a pull request, or somebody just opened up a new issue, or there was a new release, and it would send out a notification to your infrastructure. But at some point in the last few years, they added the capability for those notifications to go directly to their infrastructure, and you tell that infrastructure what to do. So immediately people started using it for unit tests, and these days I would say that's probably the primary use case for GitHub Actions. So what actually happens on the back end is GitHub will spin up a virtual machine for you that you specify. You say, I want a Linux or Mac, Windows. And then on that virtual machine, you're allowed to run basically whatever you want as a response to that event. It's completely free for public repositories. And you can have up to 20 concurrent runners. So that's a bunch of different virtual machines running at once. Yeah, as I said, what we're going to be talking about today is using GitHub Actions as a continuous integration and continuous development tool, as an alternative to Travis CI or Jenkins, if you are familiar with those. So just so we're all on the same page, what is CI and CD? CI stands for continuous integration. It's basically where you automatically run all of your unit tests whenever a change is made to your code base to ensure that nothing breaks. And unit testing, just so we have the definition out there, is a program that you wrote to exercise your code to test it. Typically in Python, those unit tests are run with the PyTest library. Continuous deployment or continuous delivery, I don't know, I've seen both. I think both are acceptable. Is the automated process of deploying your new changes after your tests pass. So typically, as far as the Python community is concerned, as far as HelioPython community is concerned, that's probably the automatic deployment to PyPI or Conda. And I have examples of both continuous integration and continuous deployment in my repositories that we go over later. So how can you get started using it? So GitHub automatically looks for a YAML file in your .github /actions directory in your repository. And that YAML file just contains a list of steps or actions for the GitHub servers to use to do once that action is triggered. There's actually also, since I started using GitHub Actions, there's a page that if you click the little Actions tab in your GitHub repository, it recommends actions to you based on knowing what kind of code that you have written. Like if it looks like a PyPI package, it recommends like, hey, do you want a GitHub action to deploy to PyPI automatically? So we'll take a look at that page later. So you can have multiple YAML files inside of .github /actions. And each YAML file will be a different workflow, and they'll run in parallel. So for CI/CD type workflows, what you do is you set the trigger to something like, okay, any push to this repository, even if it's on a different branch or whatever, run this set of tests. Or maybe any version number increase, run this deployment process. And the output of all of your actions are located in the Actions tab, so you can easily see the status of the actions that you've pushed. Some kind of cool things. Oh my God. Sorry about that. My phone does this weird thing where it jumps back in time an hour, and it thinks it's 8:30 and my alarm's going off. Okay, anyway.
Sounds convenient.
What's that?
I said that sounds convenient.
Yeah. So 8:30, my alarm's going off. It's 9:30. Okay. So where was I? Oh, so neat things to mention about GitHub Actions. So instead of rewriting scripts that other people have written a lot, there's actually these pre-built actions that GitHub has available in like a public repository that you kind of import into your code. You say, I want to run this action that pushes to PyPI or pushes to Conda. And you don't actually need to write any code yourself in that case, or write a shell script or whatever. You just say, this is the action I want to take. And here's, my configuration of that action. There's actions to install Python, to check out the code, and all of these things I use in my code that we'll see in just a minute. And these actions are actually apparently where GitHub Actions gets its name. You don't need to use these public actions. You can create your own, so that way you can reuse them between your different projects and your different workflows. And another neat thing to mention is you can set up GitHub Actions to run your unit tests in parallel with things like different Python versions and different operating systems. So you can say, I want these unit tests to run on Python 3.6, 3.7, 3.8, 3.9, and I want them to all run on Unix systems, Mac OS, and Windows. So I figured we'd just go straight ahead and go take a look at some of the YAML files. So let me end. Okay. So here is my zoomed in screen. So this is the PyTplot GitHub repository. So you can see here, I have a folder called .github/workflows. So if we click that, here are the 3 different workflows that I have set up: a unit test.yaml script, something that'll push to PyPI, and something that'll push to Anaconda. So let's just take a look at the unit test script real quick. So here is the YAML file. It's not very big. It's all right here. So let's go through each step here. So first, just the name. This is what I'm calling it: build on push. So it defines what your trigger is. So this is saying whenever there's a push to the repository, run this job. And then here's the actual definition of the job. So I'm saying run on the latest version of Ubuntu. Here's the list of steps I want to take. So here is a predefined action that comes with GitHub Actions. So I'm saying just use the action checkout. So check out my master branch. And then I've created a step here called install dependencies. Can you all see that? Let me zoom in a little bit more. And in order to do that, here's just a shell script that I run just before any unit tests run. I download Miniconda and I start installing a bunch of things that PyTplot needs. This is somewhat of a complicated example because PyTplot, in order to make the plots properly, needs a bunch of graphics libraries that don't come standard on headless Ubuntu servers. But also just installing a bunch of Anaconda libraries. And then finally, the final step here is just simply running a unit test. This starts the graphics up for PyTplot. And then I change into my GitHub workspace, And finally, this is really where the majority of the stuff happens, is just, oh wait, no. Where's the actual, oh, there it is. The PyTest script. How does this work? Oh yeah, that's right. So this is just needed for graphics to start, but then this is actually where PyTest is run. So I run PyTest against the test folder in my GitHub workspace. The CDF library does a very, very similar thing. It's a little bit more restrictive on what starts the unit tests. So here is the CDF lib unit testing script. So its name is just CI for continuous integration. And instead of on all pushes, instead it only pushes, instead it only triggers when Python files are pushed. And here you can see an example of running these unit tests on multiple different operating systems. So you can specify, okay, runs on this matrix dictionary here, and then you define the matrix dictionary a few steps down where you say, okay, I want to run on the latest version of Ubuntu, latest version of Windows, and the latest version of Mac OS. And then the steps here are very similar to what we saw before. First, I want to use the predefined action checkout. Then I want to use the predefined action setup Python, Python version 3.8. Though if we were being fancy, we could say another matrix checkout version 3.6, 3.7, 3.8, and 3.9, and run all those tests there. And then finally run the PyTest script. And then we also have a few other things here for checking the code coverage of our unit tests and uploading them somewhere where we can get a little badge output that says, oh, you have 98% code coverage, and then we can put that in our GitHub repo.
Can I ask real quick,
Yes.
where are you putting the secrets for like like passwords or whatever that needs to be pushed?
That's a good question. Did it show up here actually? Where's secrets? I was hoping to go over that as we saw them, but I don't actually see where the secrets are. So anyway, so the secrets live, if we zoom out here, if you're the owner of the repository, if you go into settings, and then down here to secrets, so repository secrets. So these things are my Anaconda token, which I need to be able to push to Anaconda, and my PyPI password. So you can add a new repository secret, and you type in what your secret name is, and then just give it a value somewhere down here. So that way, when you run your GitHub actions, that secret is stored as an environment variable, and it references that environment variable, and you can pass that into GitHub actions for your password or token needed to push to Anaconda. Does that make sense?
Yeah,
Okay.
cool, thanks.
Yep. Let's see. So I've still got a bit of time. So let's take a look at the PyPI build that I have for PyTplot. So what this does is very similar to the unit testing. I just call it name build on push. Whenever I push to master, it'll run everything. Actually, this is pretty messy here. So what this does actually is run all my unit tests again, and then assuming that passes, down here is the actual new stuff. The next step is publish to PyPI. There is actually a built-in GitHub action that is basically runs all of the publishing stuff for you, all of the necessary shell scripts to publish to PyPI. But I do have an if statement here. I say only do this step if I've pushed up a new tag. So typically how I release the code is once I'm satisfied with where it is currently, I tag my master branch and I say, this is now version 1.1. So GitHub Actions listens and says, oh, the latest of this event was a push of a tag saying, oh, now we're at version 1.1. So I'm saying only run this step if I'm pushing up a tag to my repository. There are better ways to do that. You can say, only when I release the code do you run this step. That's probably how I should be doing it, but this is kind of just what I've stuck with over the last couple years. And then finally, you can customize this action by saying with, here's where you use your secrets. You're saying with password using this environment variable here, secrets.pypi password.
I'm just curious for clarification. What happens if like your unit tests fail or this wasn't a tag? Like does this action silently fail or what?
Yeah, so if the unit tests fail, so what I have running here is actually all of the unit tests beforehand. And if any step fails, then everything else after it fails. So I'm running the unit tests right here. If that fails, it never gets to the pushing up to PyPI step.
Nice, good. So just everything after the failed step does not execute.
Correct, yeah. So let's zoom out for a second. So actions can be found under the actions tab here. If you click that, you can take a look at the different runs of my unit tests. So looks like they've all been passing lately, hooray. But if you click on it, you can actually just see the output of all of the different workflows that you have set up, all the different actions that you've taken. So the output of setting up the job, of checking out your GitHub repo, running unit tests. Oh, that's a lot. Okay. This specific one was saying, oh, do I need to publish to Anaconda? No, I do not, because it was not a tag. So I just ran my unit tests and then the job was complete and it was successful. As I was saying before, it's really easy to get started now with GitHub Actions. If you go back to the Actions tab and just click New Workflow, or if you don't have any actions, I think this is the default thing that you see in your repository. You click New Workflow, and it's got these suggestions here saying like, oh, it looks like you've got a PyPI workflow going on. So why don't you set this up with GitHub Actions? So it'll automatically like set up a YAML file in your .github/workflows directory, and it's already got a template here with name, on release created, blah, blah, blah. It does basically everything else that you guys have seen from my other YAML files. But yeah, so it's super easy to get started. You just basically need to insert your own secrets into the settings tab over there, and you're kind of good to go. Let's see, was there anything else I wanted to show? How much time do I have left? Probably not much.
Looks like you're pretty much out.
Okay. Yeah, I can't remember. So yeah, that was basically everything I wanted to show you. There, I mean, it's very, very well documented. You could go to getting started with GitHub Actions on github.com, and it goes over a brief tutorial and it gives a very clear overview of how to use it. Okay, so any questions? All right.
Well, thanks, Brian.
Yep.
Let's see. Up next, I believe we have Sean with using Git.
Yes, we do. So I could go ahead and share my screen here one moment. Oh, this is interesting. I'm doing a split screen and it doesn't want to share both of them at the same time. Let me see if I can change its mind.
No problem.
Let me see here. All right, I don't have any. I think I just have to share everything and then just navigate over to it is what it's going to want me to do.
No problem.
So, share desktop 2 is what we're looking at. And then, all right, people should see Git tutorial and then an IntelliJ window.
Yep.
Oh, wonderful. Let's see. So I'll start this out by saying that, yeah, this is a tutorial on using Git, and it's pretty beginner. This is just an introduction here to Git and a little example of walking through it. You know, how to make a Git repo and how to commit things to it. So a lot of you use this in your daily lives, and it might be very repetitive. So feel free to tune out, I guess, if Git is a bit too basic for you. But if you've never heard of Git before, or just feel like getting a refresher on the basics, then you're in the right place. So maybe I should go ahead and ask really quickly, is there anybody in here who actually does not have experience with Git? Could I get maybe someone to drop something in the chat if that is the case? Alrighty. I'll keep tabs on that, but I'm glad to know at least one person said yes. So I could spend more than 20 minutes on this, so I'll go ahead and start pushing through it here. So Git was created in 2005. Fun fact. It feels like it's been around for longer, but it was the Linux community who used it as an alternative way to handle developing all their thousands of files across their thousands of developers. Nothing around was quite doing it at the moment. And Git is a way to version control things. So we are worried about versions of files and repositories. Versions in Git form a line that's called a branch. Conceptually, you're usually seeing it written out like this, where one node points back to the one before it. That's saying that version 1 came from version 0, version 2 came from version 1. And they're called branches because that's what they do. You have various versions of your repo at any given time that branch off into kind of a tree of versions. And there's usually one main branch that people care about. This is the whole main branch versus master branch that we've talked about a little bit at some of our telecons. And then you can have feature branches or other kinds of bug fix branches, just any other line coming off of it. And what's useful about Git here is that it's cheap and easy to create these kinds of branches. You're encouraged to do it often and all the time. Generally speaking, for any new feature you're going to add, you make a new branch to create that feature and then merge it in once it's ready. And every copy of the repository is official, which is opposed to, say, SVN, where there's one centralized copy of the repo that everyone has to check out and refer to. In Git, every copy is official, and you can synchronize copies between developers. There's 3 key concepts at the root of this here, which is you have a repository, and you're going to check out your repository into a working directory, make your changes as needed, then stage your changes to a staging area. And then once you're happy with your changes, you commit them back to the repo. This workflow repeats, and that's the cycle of Git. There are many common commands that you'll be using, and I won't stop to linger on all of them because you wouldn't memorize them immediately anyway, and I've posted these slides, so feel free to go back and reference them later. But importantly, git init is the first command you're going to use inside any directory to create a Git repo. And it creates a subdirectory that will be hidden when you first create it, that stores all the files Git needs to know to work. Git commit is how you're going to be saving changes to your repo. You can view the status of your repo at any given point, because it's important to know if you have, say, untracked changes, or if you've staged a change but you've yet to commit it. And we'll see examples of all these other codes being used while I'm doing my walkthrough. So we could get to it. Stop me if you have any questions, but otherwise, here's the part where you could bust out a terminal window and follow along with me if you felt like doing so. I'll pause for just a moment for you to do that if you feel like it. I'll be using the terminal window over here in IntelliJ, and the only reason I'm doing this in IntelliJ is because it'll have a nice visualization of our Git tree that I'll reference, so it'll just be nice to do it this way. And we'll recreate basically this graph here, where I guess just to give you a preview, we start with an initial state here, and we're going to pretend like we do some development and we get some ways along, a couple commits in, and then we realize there was a bug. So we're going to go all the way back to the beginning, and then we're going to make a new feature branch to fix this bug. We're going to merge it into the main branch, and there's going to be a merge conflict. So we're going to see how to resolve a merge conflict the right way. That's maybe the most annoying part of using Git. So here we go. Here's where you would make an empty directory. I've already created one, so I'm not going to be doing make dir example project or CDing into it, but start off by creating a README. And we will just put something in here. I'll do example project. And then we're going to do, here, let me show this first. I will ls, and you can see all we have in here is this README. And then I'll do git init. Do it again, and now we have this .git subdirectory. So this is now a Git repository, and we are well on our way. You can say git status to see the status at the moment, and we will see what branch we're on. We're on the master branch. We've made no commits, and we have this untracked README file. So to tell Git to track this file, you're going to add it to the staging area, and git add is the command you'll use for that. You can either type in the name of the individual files you want to add, or a trick is you can do git add dot, and that adds any unadded files where you currently are. So I'll be using that shorthand. And then if we do git status again, you'll see that this is now green instead of red, and we have changes to be committed. So you use the git commit command to commit these things. You would normally pass it this -m flag and type in your commit message right here. But if you don't, it actually will prompt you for it. And I'll show you what that looks like. If you just type git commit, it won't let you move on before you give it a commit message. You have to describe everything you do in Git. So let's call this initial commit. And woohoo, we've now made a permanent change to our repository. We can use the git log command to see the commits that we've made. We're only seeing one at the moment. In Git, every commit has a hash associated with it, and there are these really ugly strings of letters and numbers. but they're unique to this moment in time for this repo, and we can always refer to them later, which is really useful if you want to refer to an older version in your version controlled repo. You better have a good way to do it. So let's start making changes here. We would go back and open up our README and make one change to it. I'll call this the first edit. And then we're going to go through staging and committing the thing. So git add, git commit, and I'll call this our second commit. And let's see, I want to be wary of my time. And we're about halfway through the tutorial here, and I could say more. So how about instead of making 2 commits per branch, we'll only do the 1. That'll save a little bit of time. I can open this visualization I have here in IntelliJ, and we can see what we've done with Git at the moment. Our initial commit was here. We created the file, and then we added some words to it. But now we're going to try to recreate this graph. So we're over here at 1 at the moment. Let's pretend we had made it to 2. We're going to go back to commit 0. So to do that, I can pretend like we don't already have that in front of us. You would git log to show our commits here. Our initial commit was this hash. So I'm going to copy this whole thing here. And then you can use git checkout, which is the same command you would use to switch to a new branch, but instead of a branch name, you can give it a hash, and you will go back to that space. You'll get a bunch of warnings from Git telling you that you are in a detached head state. That just means you did something funny and you mainly moved yourself around in time, and now things are abnormal. That's normal to see. And then let's create a branch here. So we're back at the beginning where we had just made our initial commit, and the command line command to create a branch is git checkout with the -b flag and then bug fix. So now we're not on that master branch anymore. We've made something new called bug fix. At this point, we can go back and make changes to our README. Watch this. Our change is gone. We're back to just example project, and that's what we'd expect. I will add second edit. Sorry, this is going to disagree with the slides now because this would have been the third edit, but yeah, so second edit here. We're going to add that change. I didn't type a space, git add, git commit with this M. See, we're learning by repetition here. This is the third commit. And then now you can look at our tree, and ooh, that might be a little bit hard to see with the dark purple there. But from our second commit, we went back to the beginning and then branched off over here. And now if we want to merge this change into our original branch, we're going to perform a git merge. And like I mentioned before, this is probably the most painful part in a developer's life cycle of using Git, because Git will try to merge versions of files automatically. This usually isn't a problem if, say, you didn't change any files in the original branch, you just added new ones, that's always fine. But say if you modified one file one way and that same file the other way, Git won't know how you wanted things to go together. So human intervention is required. And we did that here. So let's see what it looks like. The order of operations here is you check out the branch that wants to receive the changes, and then you invoke git merge with the branch that has those changes. So we want to go back to our master branch here. That is what receives the changes. Git checkout master. And we switch back to master. Now git merge bug fix. and you'll see automatic merge failed. Oh no, this is very scary. If we look at our README now, Git has added some cruft to our file. There's this head thing and this bug fix thing. That's its syntax for showing you what differs between the versions. Everything between head and this center line is what's on the receiving branch, and then everything between the middle line and here is what's on this bug fix branch. And we just decide how we want to resolve this conflict. And in our case, it's fairly obvious. We wanted first edit followed by second edit. Git couldn't figure that out by itself, so we tell it this is what we wanted. And then you save that. Git add again, git commit, fixed conflict. And we're done. We are back in a good state. We did that. I can get status on master branch, nothing to commit, working tree is clean. And then our little graph here, you can see now our feature branch has merged into our original branch. And then to finish off creating this little graph here, development would continue. So we could make just a very quick edit to this. Blah. Git add, git commit. And then voila, we're right back continuing with development like we were when we started. Life is good again. And there's more we could do, but that in a nutshell is the basics of Git. I am only scratching the surface here. This is just getting off the ground with creating a Git repo and then using it. One thing we didn't show is, I guess, pushing and pulling to a remote repository. GitHub is something most people are familiar with, I would assume. And it is practice, obviously, to upload an official copy of a repo to, say, GitHub, and then you'll be pulling and pushing changes between that copy and your local computer. And you always want to make sure to pull in the changes from upstream before you try to push any changes to it. But that is just a convention of Git. That is actually not required. It is a broader thing beyond just GitHub, and it is quite powerful, a lot more than I've talked about. So I will recommend, if you check out these slides in our Google Drive, these 3 links are the best documentation on Git I've ever found. The first one here is for people who like reading. It's from the makers of Tower, which I think is the best graphics-based Git application out there. A lot of drag and drop and everything instead of using the command line. And these other 2 are more interactive, kind of try it in your browser kind of things. So whichever way you learn best. And I think that was exactly the 19 minutes I had allotted. So I'll stop here for questions, and otherwise I'm done.
Thanks, Sean. Any quick questions for Sean before we move on to Rebecca's tutorial? Cool. Well, thanks, Sean.
Yeah.
If you have any questions,
That's
fair enough. If anyone ever has questions after the fact, feel free to ping people via email or in the Riot chat even. That's always available. All right. Next up, we have Rebecca with calling Python from C++.
All right. Can everyone hear me?
Yeah.
All right. So this is a partial joint presentation. So when I'm done with calling some Python software from C++, Lutz is going to come on and show how this can be extended to be called from C and then Fortran. Okay, so I'm going to talk about calling a Python module that I wrote in Python from C++. And the example is basically flying a satellite through some model data. So let's get started. Start my timer. Cool. All right, so a couple things you have to do to set this up. To avoid conflict with other stuff on your computer, you have to, one way I did this is by building a conda environment for PyBind 11, because PyBind 11 doesn't work with some of the more modern versions of Python. So I'm using Python 3.7 in this case. And then have all the packages for, in this case, for Komodo and the file I'm reading. So I'll go through that in a minute. And then you have to figure out how to embed Python into C++ using PyBind 11, which on a Windows machine was not straightforward, but we figured it out. And then you have to wrap the Python module and or function. And then you can have to return the returned Python object from your function into something you can work with in C++. Okay, so I'm on a Windows machine. So the instructions that I have here are a little more complicated. I used Anaconda prompt. For Linux or Windows subsystem for Linux, you just use a Linux terminal. I have no experience with Mac, so a little caveat here on the presentation. Okay, so here are the steps that I use to create the conda environment. I'm not going to talk through all of this, but the color coding is important. The red color coding is what Komodo needs to run, and that's what my software is based on. The blue color coding is what PyBind 11 needs on a Windows machine. It's also the same on Linux. They might use a different compiler on Mac. I have not looked into that. And I'm using model data that's in a netcdf file, so I also have, where's my mouse? I also had to include this netcdf for. And remember to deactivate your conda environment when you're done. Okay. For Komodo, if you want to try to repeat this, I use the Komodo from Asher's GitHub. I had to make a few changes because the CMake compiler doesn't like the @ symbols and comments. So note to Asher. Here it is. Okay, so my directory structure. So here I have this directory structure. In this directory, Komodo cxx_1, cxx, sorry. I have my CMake list.txt. This is it right here. This is basically copied from the PyBind 11 site, except for 2 lines that are emphasized by the pink arrows. So because I'm working in a conda environment, in order for the compiler to find the correct Python version, I have to include the first line on line 4. And then because I'm on a Windows machine, I have to know the path where that Python executable is, which is this message statement here on the 6th line. So I'll show how these are used later. I have my main C++ file and my functions file where I have the Python functions actually wrapped. That'll be the main focus of the presentation. And I have this build directory in italics that will contain the executable. And then this Komodo-master is just where Komodo was installed. I also have another folder called Erie, which is where I have the model output data that I'll be reading. Okay. So here's what the functions code looks like. I'm just showing pieces of it because you can see it's a little long. So these are just the C++ import statements, C++ equivalent of import statements. The top block here, the first 5 lines are what I had to do for PyBind 11, and the other 4 are just the C++. So I'm going to skip over this func directory. This is just some information I have for people using it. But here, this bottom block shows an example of how to convert a Python dictionary where the keys are strings and the values are actually NumPy arrays, how to convert that kind of thing to a C++ map. I adapted it from a Stack Overflow question. Okay, so once that's figured out, you can actually, so I had to do that because my Python functions actually return Python directories. Okay, so for example, a sample call in Python to my function called fake flight. I'll explain what that means in a moment. Takes these inputs. Okay, so a lot of these values, starting with the 65, these are actually keywords and not arguments, which isn't shown here. It's shown in the Python code, but I can bring it up if someone has a question. But starting with the numbers, all of these numbers are actually keywords which have their own defaults. But C++ and Python 11 don't really work well with defaults. You have to list all of them. So the equivalent of this call signature in Python is in C++ is the next 5 lines. I'm not using referencing simply because I don't know how it works yet. I'm new to C++, I'm more Python and IDL. Okay, so that's the equivalent call signature in C++. And then right here, this next block is showing you how to embed Python in C++ using Python 11, and then import a module here. My module is called satellite flythrough. Okay, and here in the next block is where I actually call that function from C++. And the notation here is because here's where you see the difference between the arguments in Python and the keywords in Python. So this first line has all of the arguments. Okay, notice there's no equal signs or anything like that, just like in Python. But the next several lines all have, or all keywords, and they all have default values. And they have to be referenced by their keyword names. And the way that's done is just putting quotations around the keyword name and an underscore A to tell Python 11 that this is an argument name, and then the value comes afterwards. And it's the same for all of these different keyword arguments. So the slightly irritating thing here with calling from C++ is that you have to list all of the arguments in the same order that they're defined in your Python code. You can't skip anything like you do in Python. You have to have all of it there. Okay. All right, so once that's done, this first line of the final block here calls the conversion from the Python dictionary to the map. So it takes this results object, which is a Python object. C++ can't work with it yet. It runs it through the function I showed earlier and converts it to a C++ map, which is then returned from this function. Okay, so this is an example of how to wrap a Python function with C++ when the function returns a dictionary. And the notation is the same for if it returns anything else. It's just this conversion will be a little different. Okay, so this is how to actually use the function I just showed you. So here I have to define all of the required inputs, right? Start time, stop time, the model name, file directory, and variable list. All the other things have the defaults that I just copied from Python. But so I define all of these things in C++. And this is just a print statement to check my sanity, right? Then I call the function, and notice that this function is, just for demonstration, I print a few values from this C++ map. Okay, so now this data is now in C++. I lost my time. Okay. So I print a few values just to show that it's not in Python anymore. Okay, so how do we actually run this? So there's a few different things to do. It's a few different things that I figured out with the help of Python 11 developers, mind you. Okay, so on Windows 10, these are the statements that you run. You activate your environment, you build it, and then we'll work on executing it in a moment. So what's highlighted in red is the difference between the Windows 10 and the Linux commands here. So for on Windows 10, you have to have this notation on your build command. Sorry, before the build command, sorry. And you have to actually set the Python home variable, okay, no spaces. Okay, that's just for looks. There's no spaces in this command, it will error. And then because I have plots in my software, and I haven't figured out the interactive plotting from C++, I just set my matplotlib backend to be ag, which is non-interactive, but still produces my plots. Another difference here is that on Windows 10, it puts the executable in a debug directory rather than just in the build directory as it does on the Linux side. Okay. Now, one thing to note here that you might see me do is because I've changed the Python home variable, I have to change it back before I deactivate my environment, or it will break. You won't be able to leave. It's like someone like walking in the door and you blocking it and trying to leave. Okay, to show what this looks like in code, Here it is. I'm moving to the directory where I have all my data and all of my C++ stuff. Activate the directory. Here's my build command, and this is what it spits out. Here's the Python path, and this is from the C all the way to this last / is what we use in a moment. And it prints this statement also, this found PyByte 11. Notice that this is in the directory of the environment I activated, so it's finding the right PyByte 11 and the right Python. Okay. Next, it builds it, and it puts, then I changed the Python home to this directory, which I said was up here, where it says Python path. Okay. And I have errors to show where that is. Okay, then I actually run the function from Python in C++. So here's my sanity print statements. Now, this stuff is output from Python, and it's outputting that because I'm producing plots. Those are some of the values that I have. So it's output plots. Okay. So all the Python prints to the screen, and that code also prints to the screen in the terminal here, this Anaconda prompt. This piece is also from Python code. So what's happening here in the Python is that it's generating a sample satellite trajectory because I don't have the real stuff working quite yet. And then it's taking any times that are close or within half a time step of one of my model files and adjusting it to be in the nearest file. So that's what this is. And here's another sanity check. It's printing my time range, and this is timestamp in UTC. Don't worry, the plots are more interesting. It's generating more plots here, and this is actually generating plots for the satellite fly-through part. So that's where it's flying the satellite through the model data. And this is the output from C++, where it's just printing the first 3 values from the array stored in the C++ map with this string label on the map. So it's printing the string labels here, and it's printing the first 3 values of the array. And this is to show that from this point on, the user can do whatever they want with this data in C++, whether they want to do some further analysis or cleaning or whatever they want to do. Okay. Here are examples of plots that it produced. So the first half, remember, generates that sample satellite trajectory, which I show here, just something where the satellite loops in altitude and wraps the Earth in longitude and latitude. And here the color just shows time. So the satellite first comes around here and then goes back around further and further. Okay, and you can see that more in these time series plots where I have time, which is the least interesting plot on this graph, right? But then satellite longitude, latitude, and height. And I have some some very slow height decrease built in here, and some, I can't think of the word right now, but where it wraps around in one orbit, it executes one orbit in less than 90 minutes or more than 90 minutes, so that you see this orbit sliding across in longitude. Okay, fine. But the next thing it does, it actually takes that satellite trajectory and flies it through the model data. So now here I have a 2-dimensional plot because total electron content is not dependent on altitude. So it's only showing latitude versus longitude. But the color now indicates the actual model data values at that position and time for the satellite fly through. And here's an example of what the satellite would actually see if the satellite were actually flying through those exact conditions. And then the longitude and latitude. And you don't see height again here because TEC is not dependent upon vertical. So what's coming next? I'm trying to leave time for this. The next piece is to actually make the real satellite trajectory stuff work by calling that stuff from Happy and from CEDAWeb, adding a data output routine so that the data from the fly-through can be saved to, say, a netcdf file or something like that, so the researcher can work on it later. Now we want to also call this from C and then Fortran. There might be a way to call it directly from Fortran using 4Py for integration into other codes. Okay, from here, Lutz is going to talk about calling this from C and from Fortran now that it's in C++. That's not completed yet, but he knows has a good idea how to do it. But before I move on there, would this be a good time for questions since I have my presentation up on this part?
Sure. Anyone have any questions for Rebecca? All righty. Well, then I guess we can move on.
Okay. So Lutz, would you like me to share your slides or do you have that ready?
If you can share my slides, that would be good. Then I don't have to switch around. Okay, so you have.
There you go. Go for it.
Okay, so there's ways to call a C++ function from C by simply declaring it extern C, and then you can. Here's an example for a model interpolator that was developed in C++. It's the GUMX magnetosphere model, and so on the left, in the blue is the C++ code, and then we have also a header file that can be called from both C source code and C++ source code that's on the right, and so you would define a function as external for C. So the C++ compiler will make sure that the symbols are defined so that the C compiler can actually recognize them. Because if you have C++ object files, there's a lot of additional strings and codes, and you wouldn't see the interpolate underscore HC as a symbol by itself. It has a lot of additional code in it. And so if you declare the extern C, then you can have a simple program that would then call interpolate C at HC and then uses the list of parameters. And disadvantage, of course, is if you have plain C code, you have to supply the parameters in exactly the same order, and you don't have optional parameters or keyword parameters. So you have to write an interface function in C++ that you then call from C to maybe have some logic that would call keywords as they are needed or not needed. And then the step is that you would use the C++ compiler as the linker to create the whole executable. And in a similar manner, you can do it for Fortran. So if you can bring up the next slide, Rebecca. Sure. So I have some examples here for how you call a Fortran function. You have on the right, in the gray box, is the Fortran source code for an example function. It has the function read GGCM3D B1 grids, and has a bunch of parameters again in a certain order that you have to replicate in your declaration in C. So on the left side in the blue, there's the appropriate declarations in the C compiler or C source code. And you notice that at the top here, there's two declarations, one with two underscores at the end. So this symbol name B1 read GGCM 3D B1 grids can either be followed by a single or a double underscore. That depends on the Fortran compiler. And you can even, I think, modern compiler can be directed to say like, to supply only one underscore or two underscores. And so you have to declare it with this additional underscore so that's how the symbols are created in the object code or object files from this Fortran compiler. So that's one different. And the other thing to note is that all parameters in the Fortran code are by reference, so that translates to pointers in the C declaration, and that's all it should take to invoke a Fortran function from C, or the other way around as well. So you would call a C function. So here I have an example of calling photon from C, but the other way around should work in a similar manner. So you have to declare C functions with pointers so that Fortran can properly call them. And then when you link things together, you use the Fortran compiler to link the whole thing. Or if you have to use the C or C++ compiler, you have to add Fortran libraries like gfortran or libg. There's some. So I don't have that in these slides, but yeah, you might have to include Fortran, runtime libraries. And so that's what I have for coupling C and Fortran code. And so Rebecca will use steps like that to extend the capabilities so that Fortran code and C code can also invoke the C++ functions she had presented. Okay, that's what I have.
Okay, I'm gonna stop sharing my screen.
Thanks, Lutz and Rebecca. Does anyone have any quick questions for them before we move on to our final tutorial? All right. Well, Asher, and I'm not sure if you have anyone else presenting with you, but you are up next on commodifying or functionalizing datasets.
Hey, thank you. Am I presenting right now, or how is?
We see you.
Okay, you see me, but not my screen. Okay, I just need to share this. All right, do you see this slide now?
Yeah.
Okay, cool. Yeah, so this is going to be a little bit more high level, I guess. We are going to get into some actual data, but this sort of the purpose of this tutorial is to sort of describe this function, what I'm calling functional data, or functional data science, if you will. And this cursive F is sort of an indication of like kind of where it's going in terms of like the functions in terms of both Python functions, but also more like things that we're comfortable with in math and physics. So while we're going to use Komodo, because Komodo is built around this functional approach, the concepts are very general and are meant to be like, here's this way of doing things, and we found it useful for building our product, or our products, and I think that we would benefit from this sort of paradigm. So yeah, so first I'll just start with, why do we care about functions? There's at least 3 reasons. Number one, in physics, we deal with numerical solutions often, but they are really discrete approximations of real world functions. So while this data kind of lives in these giant bricks, we actually, they're sort of just a proxy for what we actually want to illustrate, which is why we use graphs and plots to sort of illustrate the continuous nature of these things. And the discrete nature is also useful too. But kind of what we're really trying to get back to is this notion of a function that we're trained to use as physicists. And so often the other problem that we run into is that we want to evaluate these solutions at some other place and time than the original raw data was presented to us. So we want to be able to recontextualize this information. And then finally, math is the language of physics. We write a lot of Python, but which is great for doing data science. But when we're trying to communicate our ideas and train new people in the field, we sort of are like, well, you've got this whole training in math, and we just sort of ignore that for a few years while you're writing Python code. And it's sort of a shame that we've sort of just left that behind in some ways. So this is a way to sort of bring back that intuition that we had as youngsters. Unfortunately, it's not that easy. We often are just like given like a brick of data. Like here's this variable called row, and it's in an NumPy array. That's nice, I guess. And then it has some grid associated with it in this case. So this is there's no metadata showing like what these values are, but maybe this is X, this is Y, and this is Z, and then I could sort of do some look at the shapes of these arrays, and then I could start to try to build some kind of plot. So how do we, given a blob of data, just generically, how do we get to visualization, or how do we get to the actual, the meat of what we're of this information? And so I'm sort of saying that I sort of observed that, we basically have 3 ways of dealing with this. And they're also kind of historical. So the first way, we look at the data and the metadata. So that comes down to, and I'll explain each of these in detail, and we're going to focus on more of the last way. So the first way, and actually just to jump to the end, we actually need to use all 3 of these things. We're going to see how, once you've got this paradigm, you can get the best of all of 3 things at the same time. So let's look at like the data or metadata approach. So what this is really about, I think, primarily file formats. So on the one hand, you've got like HDF, CDF, NetCDF, and you've got a bunch of metadata in that stuff that includes like that tells you how the arrays are connected to each other. Like this variable depends on that variable, for instance. And you've also got these like very common, much more commonly used things like CSVs, which are just text files, right? But they have these nice header lines that tell you what's in the file, and they're just ubiquitous in every field. People who aren't programmers know what a CSV file is. But you also have things like PNG, TIFF, and these are so ubiquitous that people don't even look at the metadata. They just generally just think, send me an image, and it's just a PNG, and their software figures it out. And then speaking of software, you have like all of this specialized software that talks to these file formats. And so it sort of hides all the ugliness of the actual code from the user, and they just are opening a file. They don't really think about what's going on under the hood. And then sometimes in physics, we end up with like a binary Fortran dump, which has there's an email that describes what's in here, and you just have to live with that. But yes, so this is basically how deep science was done for decades. And then at some point, most scientists kind of switch over to using Python and these more object-oriented type languages. And with that came this concept of like, let's just put everything in a class, and it's the class's responsibility for understanding the data, essentially. So in this case, this is like PySat. This is an instrument class that reads information that has been stored in a way that PySat can read it, but also PySat has just tons of classes that are subclasses that talk to these, or I guess they're technically modules, but they talk to each instrument, and it's the instrument's job to understand the data, and then it's your job to understand the class, which then creates, and we have basically 2 decades worth of great Python projects that sort of approach things this way. And this is, I'm only listing a few that we use in the Human physics community, but so like up top, we sort of have like, these are the sort of the working things, and these are like the things under the hood that these classes talk to. But then each class is sort of specialized to the data that it's looking at, and that's great. So I don't really know if these are pros or cons, but so I just put both. So like, instead of thinking about the data being versioned, which is basically what you're left with if you do things from a metadata approach. The library itself gets versioned, and so you're keeping up to date with that version of the library. So which means that features have to wait on the interface updates. So like until if you want a new feature that to visualize like some part of your data, you kind of have to wait on that class to be updated, and that is expensive because it requires like human labor, and it requires capital and time and just all kinds of things. Which so each of these projects ends up being is a very like monumental effort when you try to do it at scale. And then for each library, you have this learning curve that the user is expected to just climb. And then finally, and that's also very expensive for their time, and especially if they're coming from a non-computer science background, it can be daunting. And then finally, you have dependency conflicts. So it's like if you try to look at two different classes, like here's PySat, here's SunPy, they might have conflicting dependencies, and if you're trying to do analysis in the same environment, things are just going to break. Like just the two can't live together in the same room, even though they would like to. But so that can be a pain. Yeah, I won't say that we've solved this problem, but I think we're sort of on a path to resolving these issues. All right, so I'm going to talk about what I'm calling the functional approach or a functional approach. And it's very vaguely described, I will say. So basically you have these two steps. First you represent your data with some black box function, and then you do stuff, and then hopefully that solves problems. So let's go through this. So yeah, here's row. So instead of row being a blob of data, it's a function. And on the right-hand side, this lambda indicates it's a black box function. So you see pretty obviously this function takes three variables, x, y, and z. And as physicists, we sort of have an idea of what that means. And then it returns something, which we're calling rho, which I call it rho because rho actually has a meaning in physics, whereas in other fields, it may mean something different, but this typically we kind of know this means density actually, and because this is what's in the literature. So this is kind of what I'm trying to get us to through this tutorial. Like, all right, so what about the data? The data is just now a function output. So in this case, I'm calling a row with no arguments, and it sends out a blob, and that blob has the shape here. So right away, the user doesn't even need to really know anything about the type coming out of here. They just need to know that this function returns a thing. And then now function evaluation is context dependent. So what if instead of giving that function nothing, I gave it like values for these three variables? Well, now I get this array that has the shape that matches the things that I sent in. So now all of a sudden, this data is a lot more useful than it was before. And notice we haven't invoked any classes. We haven't done anything like that yet, or the user hasn't, which is kind of the point. So now, if we're thinking about functions, we can sort of design interfaces that are built around functions only. And so, like this interface, this Komodo interface, is instantiated on this object that I'm calling K, and it has a method, but all that method is getting is the name of a function and a value to give it for z. And then right off the bat, it returns this thing, which is like an interactive plot where it's clearly a slice at z equals -5. And so this is it's like one line. It should be very intuitive what it means. And then this plot is, has this tells you that this is what that function is. All right, so how do we functionalize raw data? How do we get to that step? So we have several options. Let me look at my time here. I have like 20 minutes. So we have three things, like at least. There's interpolation, extrapolation, and then machine learning, which is something else. I don't really, I mean, I dabbled in it, but basically machine learning also deals very heavily with functions. So you can plug into things like that theoretically, easily, or hypothetically. So, but interpolation is typically what we're trying to do. Extrapolation is more like if you think about prediction, where you have a data set that covers a certain span of time and you want to extrapolate out to some value in the future. But what we're going to talk about here is interpolation. And for like many problems, you can sort of look at SciPy's library and find things like the regular grid interpolator, which covers like so many data sets that, because if your data set fits on a grid, this is like the thing that is most useful. Also, of course, Xarray has really great parallelized grid interpolation as well. But for now, we're just going to talk about using the regular grid interpolator to interpolate some data, specifically the IRI data set that Rebecca mentioned. And so this tutorial is kind of based around her notebooks that she sent me last night. So I basically have been working off that here. So first thing is we're going to import the regular grid interpolator from SciPy. And now we need to load some data in. So right off the bat, we were like, all right, we have this data set. It's in netcdf format. So it's this blob. It looks like this. It has this metadata. So now we're going to say like, okay, how do we make this? How do we visualize this blob? So first, we're going to load in the axis data. So we're going to this metadata says that it's dependent on these variables. So so we're just loading those variables into variables, loading the data into variables. And now we can initialize the regular grid interpolator object. The order of these things matters. And we're saying like, this is what happens if you go out of bounds. We don't want to break our Python script. So we're just gonna just return a nan if you go out of bounds. So then this is the 3D data. This is the one-dimensional axis data. And now, so this thing that we just instantiated, it has this call method, which means that you can treat it like a function. So you can give it points and it'll return you values. So here's this test point, which I'm just taking from that as basically the midpoint of the domain. And when I call this this interpolator, I get back this value. Does everyone follow so far? Before I go on, if there's anybody want to chime in. Okay.
Haven't lost me.
Did I lose someone? Oh, I haven't. Okay, good. All right, so now we can, like, this is actually just showing a little bit of how fast this function actually is. So let's say we give it like 1,000 points. I can put it in this time it thing, and then it tells me that it's like 1.28 milliseconds to do this on 1,000 points. So it's good enough for government work. We can kind of just, now we can like use this to do other things. So let's, so one thing though, is that this regular grid interpolator works on points and not slices, which makes it a little bit awkward to deal with. So first, let's try wrapping it in a function that does allow slices. So that's what this function does. The name I've given to this function is you'll see in the later why I'm giving it that name. But I'm saying, okay, here's time, height, latitude, longitude. The first thing I'm going to do is use mesh grid, NumPy's mesh grid, to expand out these variables into 3D or 4D variables actually. And then I'm going to create my points by stacking those variables up into a shape that's like 4 by n. And then I'm going to call my interpolator on those points. And then I'm going to squeeze it and reshape it into the points that came in. And so now I can treat this as a slicer. So I can put in like longitude equals 0, latitude equals 0, and then the shape of this thing happens to be the shape of the two remaining axes that I didn't slice along. So that's height and time fit so this is actually a plane at these slice locations. So that's cool. We can simplify this though. Like, I mean, basically after writing this garbage 100 times, I was like, isn't there a better, more Pythonic way to handle this? And it turns out decorators are great for exactly this thing. So the gridify decorator, which you can import from the Komodo library, does that for you. So you give it like time, height, latitude, longitude. And so say you have a function that takes a single, just takes one variable. Well, gridify takes that, mesh grids it, calls your function, and then reshapes it back to the result. So this is the same stuff that we did before, but now with gridify, we can call it as a slicer. So it actually changed the signature of the function coming in, which is pretty handy. Turns out it's kind of a pain to, or it was, to write your own custom things, but now things like Forge make writing these kind of decorators a lot simpler. All right, so then finally, what about all this bookkeeping stuff? Like where are we keeping time and height, latitude, longitude? Like they're just in some global scope. The same with the regular grid interpolator. Like we instantiated it earlier, and now we're kind of like, well, where does it live? You know? So that's when what designing classes around functions, that's the job of the class. If you're going this route, it's the class's job to basically hide all the bookkeeping from the end user. So this simple class, for instance, takes the file name, here's the interpolator function, and all it's doing is just marshalling data from the imported file into these different variables. So this is just doing all the steps that we did above, but now the user just sees this simple class. So this is the class, this is the name of the file, and when they call this class, or when they instantiate this class, it just pops out. It's something called NE, and it has this function signature. So now I can evaluate that function at a specific time, and what returns is a 3D brick of data. So this is, without even looking at the documentation of what this function is, it's pretty obvious, or it should be pretty obvious to the end user what it's doing. So now that we have this like way of doing things, you can use function inspection to get away with a whole lot of stuff that usually would be very difficult to, or not, I mean, you can do it. It's just, this is an easier way to, or a straightforward way to go about working with black box functions. So for example, we can inspect like the inputs to a function and the output of a function, and look at their shapes, and then we can map that shape to a specific plotting interface. So like, for example, if I have like an n-dimensional function that it returns an output of n shape, and it takes as an input and shape of size n, then this plotting function says, okay, that's going to be a one-dimensional line graph. I don't care what your black box does to get that information. I'm just going to treat it like a one-dimensional line. So for example, so this is how Komodo does its plotting. So here's creating a Komodo object by this keyword pair. So I'm going to create this variable called tech. I'm going to give it this function also called tech, and this function there's a little bit of metadata added to this function. I'll get to that later, which tells you the units of the function, and then out pops this thing. So when I want to plot this function, I just call Komodo's plot method. But you could see how this could easily be just a plot function and not a plot method that's just called on this original function. So Komodo does some bookkeeping that's useful for other reasons, but generally, yeah, what you're getting back is this two-dimensional slice out of a three-dimensional function. And then while we're talking about black boxes, we have about 10 minutes left. So I mentioned before we have this dependency hell that we get into with our great, we have these great libraries, they do cool, awesome things, but they are very opinionated about what you have to do to install them. So what you can do if you're dealing with containerized data and you're able to use function inspection to create APIs that are more generalized, then you've opened the door to containerizing the functions themselves. So that's what the Komodo API does. So in this case, this Komodo API is talking to a server that's hosting the functions. In this case, it's a PySat server, which is really just a PySat Docker container running on my local host. And this is the name of the instrument. So what I don't actually have to install PySat to use PySat now. So, I mean, installing PySat's not that hard, but it's just another thing that you don't have to do, because once you do it once the developer does it once, then all of their users get that access if they've containerized it. So when I instantiate the Komodo object, now I get the list of things that were registered at that API. And now I can call those things as though this data was actually living on my machine. Like I can call the northern component of the magnetic field for that instrument, and I get back this pandas date time thing. And if I want to plot this function, I don't actually need to know the underlying, I don't have to give positions or times to plot this variable. I can just give it, give the plotting commands, plot this variable, and it will use the function defaults, the default inputs to the function to give you a reasonably sampled output for that result. So this is actually raw data in this case. It's just sampled down to a level where I can easily send it over the wire. So for visualization purposes, you don't need the highest resolution data. You only need what you need to graph. And then when you zoom in, you can have some fancy things that will like fetch the higher resolution just by sending higher resolution times to that function. So Komodo does a lot of, I mentioned, why would you use Komodo if you can just use functions? Well, like the Komodo interface adds some handy features such as like LaTeX expressions. So you have, say you've registered rho and V. Well, now you can create pressure that has, you can, create this RAM pressure variable as a combination of the variables that you've already registered. It also does function composition for you. So if you have like a function like P of X and you give it, and you've also registered X of T, then it will do this composition for you so that you can get the pressure as a function of time. It also does the automated unit conversion. That looks like this. So like we have that one variable TEC that we registered before. And let's say we want to get, instead of per meter cubed, we want to get it at per centimeter cubed. Well, the way we do that is indicate on the left-hand side the units that we want it to have. And on the right-hand side, this is the expression that we're giving it. So you don't put unit conversions in anymore. On this side, Komodo figures that out for you. So when I register this, it creates this new variable tech, which is the old variable divided by this conversion factor. So this is, and then we can verify that that when we call this new variable, we get the right conversion. So this is calling the old variable divided by the new variable, and we get the conversion vector back for this test point. So this is a way of doing unit conversion that actually only uses the metadata to mark up the functions, but not the results of the functions. So we don't, in this case, we're not using like AstroPy units, which, because this conflicts with how AstroPy does things, where you attach you have a class that stores the units and your data together. This separates treats units as metadata on the function rather than the output to or inputs to the function. But we have conversions between AstroPy and Komodo. So we can kind of use both of them anyway. So under development is this IRI Komodo class, but we have a lot of other classes as well. I'm just going to show you what it looks like when you're using Rebecca's interface. So this is the list of variables that come out of that option. And then if you try to plot something at a specific time, you get this lat-long plot. And then more on Komodo, there's, so this is sort of like become an effort that's spanning multiple institutions now. So there's the CCMC, who are developing space weather readers that are basically subclasses of the core Komodo class. And then you have predictive science, which that's my current employer. And we develop CoreHel. And so this is more, the Komodo part of that is in order to visualize more easily the results from this solar physics model called CoreHel and MASS. And then we have Ensemble, who are developing dashboards and containerizing things, and also supporting Komodo core development through an SBIR. We're waiting to hear back about our phase 2 there. So I think that's it. Are there any questions? Am I still back?
This is maybe a personal question, but you were at LASP before this current place, right?
I was at NASA in Greenbelt.
JK.
Yeah, but I have visited LASP on numerous occasions and given.
Yeah, I know I'd seen you around, but I
Yeah.
okay. Yeah.
Yeah, I'm getting old, so when you hang around enough, like, it seems like I'm around. But yeah, this has been an honor to present here, and I'm like, we're just sort of starting to tap into what I like to work on is commodifying like SunPy directly, and that's a lot more tricky because the image, a functional form of images is something I haven't tried to implement yet. But once we have that, then you should be able to do things like enhance, and zoom in on an image and get, but also it would let you use SunPy outside of like the Matplotlib kind of environment. So we're using, I didn't mention this, but we're using Plotly for all of our stuff because we're very web oriented, especially with like things like the containerization and dashboard development. Having the ability to like work in like leverage the web-based front end stuff is great.
You said Plotly, that's what you said?
Yeah, Plotly. So Plotly for dashboards and plot generation, and it does let you, it does have a Matplotlib converter. So if you've already done a lot of great work in Matplotlib, you can sort of convert those plots directly into Plotly for web rendering. But you kind of are better served by re-implementing it in Plotly. It's like the conversion's not that great. But yeah, this any other questions, anybody? Well, I'm uploading a version of these slides. So if you want to revisit them, right ahead.
Thanks, Asher.
Yeah, that might be a wrap.
Yeah, I believe that's it for today. So we're going to end a couple minutes early. Tomorrow we'll have hackathons. Start the day off, maybe have everyone do like a 1-minute spiel on what they plan to hack on, and then off we'll go. See you all again at 9 a.m. tomorrow morning. Thanks to everyone who presented today.
Well, thanks for everything, Julie.
Okay, thanks for having us.
Thanks, everybody.
Again.
Thanks.
See you guys
Bye.
tomorrow.
All right, bye.
Tomorrow.
Bye, see you tomorrow.